Hello everyone, and welcome back to another video by Endless Engineering. Today we're going to be implementing logistic regression in Python from scratch to do some handwritten digit classification. We're going to be using the gradient ascent algorithm, and if you're not familiar with this algorithm, I recommend you go back and watch my video that details all of the derivation for this algorithm, because I'm going to be using the same notation here and you might not be able to follow along. So essentially what the gradient ascent algorithm does is it updates this parameter theta using this term right here, which is derived using the approach of maximizing the log likelihood function. And this is the log likelihood function, which we derived in a previous video using a Bernoulli distribution. And h here is the sigmoid function, which is our hypothesis. Theta are our parameters, and x bar is the feature vector augmented by 1. And essentially in this video, what we're going to be implementing is the batch gradient descent or batch gradient ascent. They're really the same algorithm. And this algorithm basically loops through a number of iterations, and in every iteration it's going to go through the entire data set and keep updating the parameters. And in a previous video when I talked about gradient descent with linear regression, I mentioned that this might not be the greatest algorithm to use for large data sets. However, you'll see today that it pretty much suits our need. And that's really the key of using any machine learning algorithm, is that you pick the algorithm that works for you and for your problem. And recall that the logistic regression problem is essentially a binary classification problem, but we have 10 digits that we want to classify, 0, 1, all the way to 9. So this is a multi-class classification problem. And the way we're going to be doing that is what I like to call the brute force approach, but it's referred to as the one versus all or one versus rest approach, where if you have n classes, in our case we have 10 different classes, then we will train n different classifiers, in this case 10 classifiers, and when we get a new data point and want to predict what class it belongs to, we run all of our 10 different classifiers and we pick the one that has the largest probability. But it doesn't matter in this case because we're going to build one kind of classifier, which is a logistic regression classifier, and we can then reuse it for whatever number of classes that we want. Now this might not be the best way to do multi-class classification, but you'll see in this video that it's simple enough, but it gets pretty good results. So let's start. So I'm starting out here by some code that I've written before. I'm importing the digits dataset, which is in sklearn datasets. And I'm also importing the train test split from sklearn as well. This is going to help us split our dataset. Importing numpy, of course, and pyplot so we can plot stuff if we want to. This is our first plot here where we're going to see the digits themselves. So I just basically took a couple of data sets here and plotted them to show you what they look like. So they're not really that clear to us. And again, remember, these are 16 by 16 images, right? So they're very small and they're not really great quality. But again, this is an example that shows you this is actual real world data where we're going to take handwritten digits that have been digitized into images, and we're going to write a logistic regression class here that is going to allow us to classify these digits. So I've pre-filled out some functions here so that we can code them together. So this is a class that I'm going to create that's called Logistic Regression. And it's going to basically allow us to train on a data set and then predict however we want. And we're also going to be able to measure the accuracy of our classifier. So let's start out with this set values function. So there's a bunch of values that we need to set essentially for the classifier to be able to do its job. The first is going to be the parameters. So the parameters here are passed in, so I'm going to store them as a member variable here in params, and also alpha, which is my step size in the gradient ascent algorithm. I'm going to store that in here as well. There's also the maximum number of iterations. That is defined by the user, so we have it in our interface as well. And here I have another parameter called class of interest. And I want to stop here and talk about this for a second. So class of interest in this case is basically because this logistic regression classifier is a binary classifier. So it can either tell you if the class that it's classifying is a 0 or a 1. So it can either tell you that whatever data point you gave it is the class that it knows how to classify or not. And in this case, let's say we're going to train to learn the digit number 8. So the class of interest that we would pass to this classifier would be 8. And that way it knows that it's going to learn number 8 And anything else that it sees is going to be a not 8, essentially. And this goes to the concept of one versus all, right? When we train 8 different classifiers or 10 different classifiers, they're all going to be trained on a class of interest, and they'll be able to identify that class of interest. And essentially, when you pass it a image and it's going to classify it, then it's going to tell you the probability that it is the class of interest or not. And then you pick the one with the largest probability out of all of your classifiers. So our next function here is a sigmoid. So this sigmoid function is very important for our hypothesis, right? So I'm just going to code it right here. So it's 1 divided by 1 plus the exponential 2 minus x. Right? X here is the input to this function, so it doesn't have to be the actual x of features that we have. I'm just calling it x. And I also have a predict function. Now this function is going to let us use the sigmoid function so that we can predict the output or the probability that something belongs to, some input belongs to a certain class. And I'm going to use the sigmoid function here, and I'm going to do a dot product. I don't know why I can't type today. NumPy dot product, and that's going to be between params and x, the input, right? So remember here also, actually, this won't be x, this will be x bar, right? So to predict, we're going to have like x bar, and we're going to do a dot product with x and x bar, and we're going to take the sigmoid on that, and that's going to give us the probability that something belongs to a certain class, right? That's a prediction for a probability. Okay, great. Our next function will compute the cost. And remember, the cost here is essentially the likelihood, the log likelihood cost, which we defined earlier. Let me scroll up back there. This is the cost that we have, right? It's the sum over y, which is the label itself, multiplied by the log of our hypothesis, plus 1 minus y log of 1 minus hypothesis, right? It's a very nice function. It assumes the Bernoulli distribution, and it allows us to do this binary classification. So let's go ahead and write that here. So say we have our input variables and our output variables and our params. And remember, this is the entire data set, right? Every time we want to compute the cost, we pass in the entire data set. So let me say that we have to loop over the data set itself, zip with input var, and output. Well, in this case, the output variables are going to be the labels themselves, and say x bar here. Remember, we have to augment our input from the we have to augment our input of the features with the 1 on top, right? So we can have a bias term, right? That we train and we find. Okay, so now we have y hat, which is our prediction, right? We're using the function that we wrote to predict x bar and params. All right, so that gives me my predicted value, and now for me to compute the cost itself, right, I need to do a sum. So outside of this loop, let's just define a cost equal to 0, right? And then we will add to that y. Okay, so this is important here. Let me call this y binary and multiply it with, let's write out the log likelihood first, and then I'll explain what that binary, y binary is essentially. 1 minus y binary, let's put 1 like that, multiplied by the log of 1 minus y hat, right? So just to clarify what I mean by y binary here. So this is essentially the binary class that we are trying to classify, right? And what do I mean by that? Remember when I told you that we're passing in the param class of interest? So this is the class of interest we're trying to train on. Again, this is a binary classification problem. So for us to know what y binary is, it can either be a 0 or a 1, right? So we'll say that y binary is a 1 if y is the class of interest, right? Else this is going to be 0, right? So in this case, if say I'm trying to learn the digit 2, then if y is equal to the class of interest 2, which is coming from the label, then my binary y is equal to 1. Otherwise, it's going to be 0. So it's 1 means it's definitely the class of 2, digit 2. Otherwise, it's going to be 0. And I'm going to use that in my cost, which is the binary y times the log of the predicted value of the probability, plus 1 minus y binary times the log of 1 minus the probability. Right? So this, I'm going to basically keep summing over this cost, and I return this cost over here, right? Okay, so let's recap real quick. What did we do? We basically started out this class as setting values for my initial parameters, for my alpha, for my max iterations class of interest that I want to train on. I defined a sigmoid function, and I defined a prediction function that allowed me to do the prediction of the probability given an input that it belongs to a certain class. And I'm computing the cost using the log likelihood function. Okay, so now we need to write a function that allows us to train based on passed in data, right? And this is, again, coding the batch gradient descent, right? So let's start out with an iteration. Let's say we're in iteration 1. We're going to start from there. And let's say that while my iteration is less than my max iterations, right? That's how many times I'm going to loop. I'm not going to go more than max iteration. Then what I'm going to do is I'm going to loop over my data set, correct? Because every time I get an iteration, I'm going to loop over my data set, and I'm going to say, okay, give me my predicted value and tell me what my gradient is so that I can update what that is. So zipping my input and my labels, right? I'm going to loop through them, and I'm going to say, give me my x bar, which is augmenting again here. Now you could write a function that allows you to do this. I'm just going to write it here. It's just, I feel like it's quicker. Right, so what is this doing? Basically, I'm inserting a 1 in front of my input variables, and then I'm computing my prediction. Right, I predict with x bar and my params. Right, and then I need to compute my gradient, and that's going to be equal to y minus y hat times x bar, right? But again here, what is y? It's the same concept as this y binary over here, right? We can't go and pick y as the actual label itself. So what we have to do is we have to find out y binary. And in this case, y binary, we get it from xy1, right? So if this xy1, which is essentially the label, if it's equal to the class of interest defined by the user, then the y binary is 1. Otherwise, the y binary is 0. And I compute my gradient using that y binary. Let me take this here, y binary, right? And now I can update my params to be, I'm going to use my step size, alpha, and multiply with the gradient, right? And after this is done, after I loop over this, I have to increment my iteration, right? Okay, so basically what we're doing here is we're getting an input and an out and labels to these inputs, and we have, I'll tell you what this is in a second. We iterate from 1 to the maximum iterations, and in every iteration we're looping over the data set, and we are defining x bar, which is a numpy array that's inserting a 1 in front of all of my inputs, and then I'm predicting my probability that this x bar belongs to a certain class or not, and then I'm computing my y binary, which tells me that in fact this data point is labeled as the class of interest or not, and I'm using that to compute my gradient, which I then use to update my params. Actually, this needs to be plus equals, so I'm incrementing. And going back to this print iteration, so basically what I want to do is I want to print my cost when I'm training so that I can see that I'm doing the right thing. So instead of printing every iteration, because we're going to have a large number of iterations, we're going to print every so often iterations, right? So these print iterations, they're set to 5,000 as default, and the user can change them. And what we're going to do is we're going to print the iteration, and we're going to say that, and we're also going to print the cost, right? And the cost is, I can compute my cost, right, from the function that I wrote. So and I need to pass to compute cost my input var and my labels, also my params. Right, okay. So let me also print like a new line, so that we can know, every iteration looks nicer this way. Okay, so now we have a function that's going to allow us to train our model, but we also want to test how well our model is doing, right? How well our classifier is doing. And one way to do that is to compute what's known as the accuracy. So let's say we're going to split our data sets, and we're going to have a training and a test sets, right? So let's just make a few variables here. So I have the total classifications as 0 and the correct classifications as 0. What we're going to do here is we're going to run our model on the test data, and we're going to classify every point. So let me loop over the input and labels, right, for test. And when I loop over this data, what I'm going to do is exactly the same thing as I did up here, right? What I'm going to do is I'm going to compute my x bar, and then I'm going to compute my y hat, and then I'm going to compute my binary. So let me just copy this here and edit it, right? So x bar is going to be like this, and then y hat is going to be x bar and params with the predict, and then my y binary is going to be 1 if my y is equal to the class of interest, otherwise it's going to be 0, right? And so every time I do this, I'm going to have to increment my total classifications, right? Because every time I loop, over one data point, I'm going to do one classification. And now that I've done this classification, I need to check if what I classified is correct. So what I can do is I can say if my y hat is greater or equal to some threshold, let's say 0.5. Right, so let's say that I want to set this threshold and say if I classify something as 50%, that means that it is in fact the class, right? If I get a probability that something is 50%, then it's in fact the class itself. And you can, you can pick that threshold however you want. Let's just start with this. And let's just say y binary is 1, right? So that means that I did get a probability that it's 50% or more, that this is a 1 binary, right? So it is the class I'm interested in. So that means that I made a correct classification. So I will increment my correct classification, right? So this is basically a correct classification of class of interest. Let's put a note here. Say this is a correct classification of class of interest. right? But there's also other cases, right? There is the case where I have a probability that is less than 0.5, right? So I have a low probability below the threshold, and my Y binary is not equal to 1. So this is not the class of interest, right? This is also a correct classification of another class, right? So this means that my Y binary tells me that, the label tells me that this is not the class you're interested in, and my probability is that less than 50% that it is the class you're interested in. So that's also a correct classification, right? So, and now to compute accuracy, what we do is we divide, self-dot. To compute accuracy, we divide the correct classifications by the total number of classifications, right? So that basically tells you the ratio of how many times you got a correct classification versus what your total classifications were, right? So let's say that you did 100 classifications and you got 10 correct. That means you have a 10% accuracy, right? Okay, let's just look at this again and see what it's doing. So this is the test function. We're passing in the test data, the test input and the label, and we're saying that we have total classifications and correct classifications. We loop over the entire data set, and we do a classification every time by computing X bar, and then we are doing a prediction here of what this X bar is using our parameters, and we're computing the Y binary. Again, we talked about this before. And then I'm saying that if my probability that this is in fact the class of interest is more than 50%, and the label tells me that it's a class of interest, that means I got a correct classification. And if the probability that it is not the class of interest, or the probability that it's a class of interest is less than 50%, and it is in fact labeled as not the class of interest, this should be a 0, right? Oh, no, that's correct. This should be a 1, not equal to 1. Then I do get a correct classification. And to compute the accuracy of this classifier, we divide the correct number of classifications by the total number of classifications. Okay, we have an error here. Line 26. Okay, so there's an in here. Okay, so now we have written a logistic regression class that allows us to train on data and test our accuracy. So what I'm going to do is I'm going to split the data set that we got from sklearn on the digits, and we saw this data set over here, right? I'm going to just split it and randomly assign it and randomly shuffle it. That's what the test train split does. And I've written some code here to allow me to use the class that I just defined to define a digit regression classifier for the digit 0, right? And I've set the maximum number of iterations to 10,000 and my alpha to 0.01. So let's go ahead and run this. Okay, so now that I've run this, I can see that I have, throughout my iterations, my log likelihood cost is increasing because this is again gradient ascent. So it starts from a negative number and it keeps going up. Obviously the maximum it could go to is 0. So we got pretty close, right? So this is good. Now what I can do is I can use my test data and I can check what my accuracy is, right? And just to make a note here, I'm dividing my input values by 16 because if you look at the data in the digits data set, then you'll see that they basically have a maximum value of 16, right? And it's usually good when you work with images to normalize the value. That makes it easier for the algorithm to work because when you have a summation in the log likelihood and when you keep iterating over your parameters, then you might get into problems with your gradient becoming too shallow and things like that. But anyway, what I'm going to do here is I'm basically going to give the classifier that I just trained using training data, right? I passed in training data here. I'm going to test its accuracy using test data. So this is data it's never seen before. And basically what this is going to do, it's going to run my test function. And what my test function does is it takes all the test data and it loops over it and it classifies. And it uses a 50% threshold to say that, whether this was classified correctly or not. and we're going to get the accuracy. So let's run this. And you can see here, I get an accuracy of 100%. That means I classified every digit that was a 0 correctly and every digit that was not a 0 correctly. Now, to be honest with you, when I first got this result, I was kind of astounded. I didn't think I would get this good of a result, but I checked the data, I checked my algorithm, and I also plotted some stuff in another notebook, and I looked at it, and it seems pretty legit. So what I'm going to do here is I'm going to train a bunch of other classifiers that are going to give me the classifier for 1, for 2, the other digits, and let's look at what their accuracy is. So now I've trained classifiers to classify the 1 digit. So in this case, you can see that we start out, we have a cost, and that cost is, negative, relatively high. It goes down a little bit, but not a lot. So it doesn't go down as much as we did for the 0 digit, right? But we still get a 97.5% accuracy on the test data. And I'm using the same number of iterations as before, 10,000, and the same step size. So this is pretty good. This is a pretty good result. So basically, you can see the cost is still going down. So if I increase the number of iterations and I played around with my alpha, I could probably get a better result than this. And I also trained classifier for the 2 digit and for the 8 digit. And for the 2 digit, I got 100% accuracy on classification. And you can see that the cost here went considerably down. And remember here, we're training on data and we're testing on entirely different data. So the data that we test on is data this classifier has not seen, or these classifiers have not seen before. So these are pretty good results, really. Now for the 8 digit, I tried, I tried 0, 1, and 2, so I jumped up to 8. We get a 96.1 accuracy. We get a 96.1 accuracy. And here, again, I'm using only 10,000 iterations, and the alpha is 0.01. So potentially I could play around my alpha, increase the number of iterations, because I can see that my cost is still going down here when my last iteration exited. And so again, this is taking a little bit of time to run. It takes somewhat of around maybe 2 minutes to run per classification. So a lot of stuff that we wrote with and if you look at the class, we wrote using for loops and things like that could be optimized by potentially using NumPy, matrix multiplication, and things like that. I just wanted to write it here in a way that makes it clear from an algorithmic point of view. But there's definitely a lot of software enhancements that can be done here that could make it faster, and it could train faster, and you can iterate and do a lot of things. But I'm really happy with the results that we got. We're getting around 96, 97% to 100% accuracy on some digits. And this just goes to show you that with machine learning, it's really all about picking the correct algorithm for you to do a certain task. Now, if you know one algorithm, if you only have one hammer, everything looks like a nail, right? But if you learn multiple algorithms and you really understand the basics and concepts of the algorithm itself and how it's derived and how it works, then you can really pick the best algorithm for your data. Now, I'm not saying that, logistic regression is the best algorithm for handwritten digit recognition, especially for a multi-class classification problem. I'm just showing you that a simple algorithm like this can go a long way in at least a first pass solution at a problem. And that's what you should strive for, is picking an algorithm that works for you, that is based on your data set and based on the problem that you're trying to solve. I hope you enjoyed this video on implementing logistic regression from scratch in Python. I'm going to leave this notebook up on GitHub, and you'll find a link for that in the description below. If you enjoyed this video, hit that thumbs up button, and think about subscribing to Endless Engineering and supporting the channel. Also, maybe hit the notification bell, that way you get a notice every time we roll out a new video. Thank you for watching.